3D scene representations for embodied agents. Cold open. Imagine handing a robot a single instruction. Go to the kitchen, find my blue mug, and bring it back. Sounds trivial. A 5-year-old does it without thinking. But for a machine, that one sentence hides an enormous problem. Before the robot can move a single motor, it has to answer a deceptively deep question. What does the world actually look like to me, in 3 dimensions, right now? It needs to know where the walls are so it doesn't crash. It needs to know that the kitchen is a place connected to the room it's standing in. It needs to know that a mug is a graspable object sitting on a surface, that it's blue, and that blue is a property attached to a specific chunk of geometry in space. All of that, geometry, connectivity, semantics, and the ability to act on it, has to be packed into some internal model of the scene. That internal model is what we call a 3D scene representation. And the choice of representation is not a minor engineering detail. It quietly decides everything: how much memory the agent burns, whether it can plan a path, whether it can grab an object, whether it can even understand what you asked for. Pick the wrong representation, and the smartest planner in the world is useless. In the next half hour, we're going to walk through the entire landscape of 3D scene representations for embodied agents, from the humble point cloud all the way to neural fields and Gaussian splats. And I'll show you exactly what each one is good at, where each one breaks, and how to choose. Let's get into it. What is an embodied agent and why 3D? Let's define our terms, because embodied agent gets thrown around loosely. An embodied agent is any AI system that has a body, real or simulated, and has to perceive and act inside a physical, 3-dimensional world. A warehouse robot, a home assistant, a drone, a self-driving car, a virtual character in a physics simulator, all embodied agents. The defining feature is the loop. The agent senses the world, updates its internal model, decides on an action, moves, and then senses again. Perceive, represent, plan, act, repeat. Now, why insist on 3 dimensions? Why not just work with camera images, like an image classifier does? Because actions happen in 3D. A path is a curve through 3D space. A grasp is a 3D pose of a hand relative to a 3D object. Collision is a 3D geometric fact. If your representation is just a flat 2D image, you've thrown away exactly the structure your motors need. 2 objects that are far apart in depth can sit right next to each other in a photo. And a robot that only sees the photo will happily try to walk through a wall that looks small because it's far away. There's a second reason, and it's about consistency over time. As the agent moves, its camera sees the same table from many angles. A good 3D representation fuses all those views into one coherent model that stays fixed in the world while the camera moves around it. This is the difference between I see a table in each frame and there is a table at this location, and I am now looking at it from the side. So what do we actually want from a 3D scene representation? I'd argue there are 6 demands, and every representation we discuss is really just a different compromise among them. 1. Geometric accuracy. Does the surface match reality? 2. Memory efficiency. Can it fit in the agent's limited compute? 3. Query speed. Can I ask, is this point occupied? Fast enough to plan in real time. 4. Completeness. Does it fill in the parts the camera hasn't seen? 5. Semantics. Does it carry meaning, not just shape? And 6. Differentiability and updatability. Can it be refined smoothly as new data arrives, ideally with gradients so we can optimize it. Hold those 6 in your mind. They're the scorecard. Explicit geometry, point clouds, voxels, meshes. Let's start with the most literal, most intuitive family, explicit representations. These store geometry as actual, listed out primitives, points, little cubes, or triangles. If neural networks feel like magic, explicit geometry is the honest, no-tricks baseline, and it's still the backbone of an enormous amount of real robotics. The simplest is the point cloud. A depth camera or LiDAR fires out rays, measures how far each one travels before hitting something, and hands you back a big bag of 3D points, just coordinates, sometimes with a color attached. That's it. A point cloud is nothing more than an unordered set of positions in space. The beauty is that it's a direct, almost raw measurement of the world's surfaces. LiDAR on a self-driving car produces point clouds millions of points strong, several times a second. But point clouds have 3 real weaknesses. They're sparse, there's empty nothing between the points, so the surface isn't actually defined, just sampled. They carry no notion of what's solid and what's free space, which matters enormously for collision checking. And they're unstructured. There's no grid, no connectivity, so asking what's near this point means searching, which is why we build spatial data structures like KD trees on top of them. To get structure, we can bin space into a voxel grid. Think of it as 3D pixels, a lattice of little cubes where each cube is marked occupied or empty. Now free space is explicit. If a voxel is empty, the robot can pass through it. This is the classic representation for collision-aware navigation. The famous variant in robotics is the occupancy grid, and the clever part is how it handles uncertainty. Instead of a hard yes/no, each cell stores a probability of being occupied, and every time a sensor ray passes through, we update that probability. The trick that makes this efficient is to store the belief in log odds form, because then a sensor update becomes a simple addition instead of a messy multiplication. That single design choice is why occupancy mapping runs in real time on modest hardware. The cost of voxels is memory, and it's brutal. Memory grows with the cube of resolution. Double the detail and you octuple the storage. Model a whole building at millimeter resolution as a dense grid, and you'll run out of RAM instantly. The fix everyone uses is a sparse tree, an oct tree, that only spends memory where there's actually surface, which is the idea behind systems like Octomap. The third explicit form is the mesh, vertices joined into triangles, forming a continuous skin over surfaces. Meshes are what games and graphics use because they render beautifully and define a real, watertight surface, not just samples. For an embodied agent, a mesh is great for a final, clean map of a static environment. But meshes are painful to build and edit on the fly because every time geometry changes, you have to restitch the triangle connectivity, which is fiddly and slow. So meshes tend to be an output representation, the polished result, rather than the live working memory of the agent. Here's the through line for this whole family. Explicit representations are transparent, fast to query, and easy to reason about, but they either leave gaps, point clouds, cost too much memory at high detail, dense voxels, or resist online editing, meshes. That tension is exactly what drives us toward the cleverer representations coming up. Distance fields, SDF and TSDF. Now, for a representation that quietly powers a huge amount of both robotics and graphics, and that a lot of people find genuinely elegant once it clicks, the signed distance field, or SDF. Here's the core idea. Instead of storing where the surface is, we store, for every point in space, the distance to the nearest surface, and we give that distance a sign. Positive if you're outside the object, negative if you're inside, and exactly 0 right on the surface. So the surface isn't a list of points anymore. The surface is defined implicitly as the set of all locations where the distance function equals 0, what mathematicians call the zero-level set. Why is this so useful for an embodied agent? Because a distance field answers questions a robot desperately wants answered. How far am I from the nearest obstacle? That's just reading off the field value, no search required. Which way should I move to get away from obstacles? That's the direction the field increases fastest, its gradient. Collision avoidance and motion planning almost want to be written in terms of distance fields, and many state-of-the-art planners are. There's also a beautiful smoothness property. A true signed distance field has a gradient with unit length everywhere. The distance changes at a rate of exactly 1 meter per meter as you walk away from the surface. That constraint, the iconal property, turns out to be a powerful thing to enforce when we later learn these fields with neural networks. Hold that thought, it comes back. In practice, we don't store the raw SDF everywhere. We use the truncated signed distance field, the TSDF, which is the heart of real-time 3D reconstruction systems like KinectFusion. 2 changes. First, we truncate. We only care about distance up to a small band around the surface and clamp everything beyond that, because who cares about the exact distance to a wall from 3 rooms away? Second, and this is the elegant part, we fuse measurements over time with a running weighted average. Every new depth frame votes on the distance value in each voxel near the surface, and we blend those votes weighted by confidence. Noisy single-frame depth, averaged over dozens of views, converges into a startlingly clean, smooth surface. That averaging is why TSDF fusion produces such nice reconstructions. It's essentially denoising by integration. The trade-off? A TSDF is usually stored in a voxel grid, so it inherits the voxel memory problem, though sparse and hashed variants tame it. And it represents static geometry beautifully, but doesn't natively handle moving objects or semantics. Still, if you want a clean, continuously updated surface for a robot mapping a room, TSDF Fusion remains a workhorse and a genuinely great default. Neural implicit representations. Everything so far stores geometry in an explicit grid or list. Now we make a conceptual leap that reshaped the whole field. What if we replace the grid with a neural network? Instead of a giant array of voxels, we train a small network whose weights encode the entire scene. You feed it a 3D coordinate, and it tells you something about that point. The scene lives inside the function. This is the world of neural implicit representations, also called neural fields or coordinate networks. Start with the simplest version, occupancy networks. The network takes a 3D point and outputs a single number, the probability that this point is inside the object. The surface, once again, is a level set, this time the set of points where the network says 50-50, the boundary between inside and outside. A close cousin is DeepSDF, where instead of occupancy, the network regresses the signed distance we just discussed. So now the SDF isn't stored in voxels, it's stored in network weights. The magic here is continuity. A neural field has, in principle, infinite resolution. You can query any point at any precision, and the network interpolates smoothly because a continuous function has no voxels to be blocky about. And one network can represent a whole class of shapes if you also feed it a latent code, one number vector per object, so the same weights, with different codes, become different chairs, different tables. That's a stunning compression of an entire object category. But the representation that truly detonated this field is NeRF, neural radiance fields. NeRF asks a different question. Instead of, is this point solid, it asks, if I look at this point from this direction, what color do I see, and how much does this point block light? So the network maps a 3D position and a viewing direction to a color and a density. On its own, that sounds abstract. The genius is how you render it into an image using classical volume rendering. To figure out the color of one pixel, you shoot a ray out from the camera through the scene, and you march along it, and at every step you accumulate a bit of color weighted by two things: how dense the scene is right there, and how much of the ray's light has survived to reach that point without being absorbed earlier. Points hidden behind a solid wall contribute nothing because the light never gets to them. Points on the first solid surface contribute the most. Sum it all up along the ray, and out pops the pixel color. And here's the beautiful part. That whole rendering process is differentiable. So you can take real photos, render the network's guess of those same photos, measure the difference, and push the error backwards through the rendering to nudge the network's weights. Do that over thousands of rays, and the network is forced to invent a 3D scene whose renderings match your photos, even from viewpoints it never saw. You get photorealistic novel views out of a network you trained purely on 2D images. No depth sensor required. That was the shock of NeRF. One subtle but crucial trick made it work. Naively, a small network can only represent smooth, blurry functions. It can't capture sharp edges or fine texture. So NeRF first lifts each coordinate into a high-dimensional set of sine and cosine waves at many frequencies, a positional encoding, which gives the network the raw ingredients to express high-frequency detail. Without that trick, NeRFs come out looking like fog. For an embodied agent, neural fields are seductive. Infinite resolution, tiny memory footprint relative to the detail they capture, fully differentiable, and, as we'll see next, they can carry semantics too. The catch, and it's a real one, is speed. The original NeRF took hours to train per scene and couldn't render in real time, which is a non-starter for a robot that needs answers now. An enormous amount of follow-up work, hash grids, feature grids like Instant NGP, and hybrid schemes attacked exactly that, dragging training from hours down to seconds. But the fundamental tension remains. Pure neural fields trade query speed and online updatability for accuracy and compactness. 3D Gaussian Splatting. NeRF gave us photorealism and differentiability, but it was slow. In 2023, a technique arrived that kept most of the photorealism while rendering in real time, and it has since swept through both graphics and robotics: 3D Gaussian Splatting. The idea is a lovely hybrid. It's explicit like a point cloud, but soft and blendable like a neural field. Instead of representing the scene with a network you have to query millions of times per image, you represent it as a big collection of little translucent 3D blobs. Each blob is a 3D Gaussian, a fuzzy ellipsoid, with a position, a shape and orientation, a color and an opacity. Picture thousands of soft, colored, stretched cotton balls floating in space, and together they are the scene. A thin, dark one lies flat along a tabletop. A fat, bright one fills the body of a mug. To render an image, you don't march rays through a network. You take each 3D Gaussian, project it onto the image plane, where it becomes a 2D fuzzy splat, and then you blend all the splats that overlap a pixel, front to back, according to their opacity. This is essentially the same alpha blending your phone uses to composite transparent layers, and GPUs are ferociously good at it. That's the secret to the speed. Rendering becomes sorting and blending flat splats instead of integrating along rays. And here's what makes it more than a pretty trick. The whole thing is still differentiable. You start with a rough point cloud, turn each point into a Gaussian, render, compare to your real photos, and let gradients flow back to adjust every Gaussian's position, shape, color, and opacity. The system even adds and removes Gaussians automatically, splitting big fuzzy ones where detail is missing, deleting ones that aren't pulling their weight. The result converges to a scene that renders in milliseconds and looks photoreal. One neat piece of math worth flagging because it's a clever engineering fix. A Gaussian's shape is described by a covariance matrix, but if you optimize that matrix directly, gradient steps can push it into an invalid, non-physical state. So instead, they factor the shape into a rotation and a scaling, an orientation and 3 stretch amounts, which by construction always yields a valid ellipsoid. It's a small idea that makes the whole optimization stable, and it's a nice example of how representation choices interact with learnability. For embodied agents, Gaussian splatting is a big deal, precisely because of the real-time rendering and fast training. Robots have started using splat-based maps for navigation and even manipulation, and because each Gaussian is an explicit editable primitive with a location, you can move objects, delete them, or attach extra information to them far more easily than you can edit a monolithic neural field. The open challenges are handling dynamic, changing scenes gracefully and keeping memory in check when the Gaussian count explodes. But as a live, photoreal differentiable map, it's one of the most exciting representations in the field right now. Semantic and feature fields. So far, every representation we've built answers geometric questions. Where is the surface? Is this point solid? What color is it? But remember our robot's task, find my blue mug. Geometry alone can't do that. The agent needs meaning fused into the 3D world. It needs to know not just that there's a graspable shape on the counter, but that this shape is a mug and is blue and matches the word you said. This is the frontier of semantic and feature fields, and it's where 3D representation meets modern foundation models. The naive approach is semantic segmentation. Label every point or voxel with a category. Chair, table, floor. That works, but it's rigid. It only knows the fixed list of categories it was trained on. Ask for something outside the list. The fragile ceramic thing, or the object I usually drink coffee from, and it's lost. The powerful modern approach is to fuse open vocabulary features into 3D. Here's the recipe, and it's elegant. We already have 2D foundation models, like Clip and DINO, that turn any image patch into a rich feature vector, living in a space where meaning is geometric. The feature for a photo of a mug sits near the feature for the word mug. So the idea is to lift those 2D features into 3D. We augment our field, whether it's a NeRF or a set of Gaussians, so that in addition to color and density, each point also carries a high-dimensional feature vector. Then we render those features into 2D, exactly the way we render color, march the ray, accumulate the feature. And we train the 3D features to match what the 2D foundation model reports for each pixel. That's called feature distillation. The 2D model is the teacher, and the 3D field learns to reproduce its features in a spatially consistent, multi-view way. Systems in this family include distilled feature fields and language-embedded radiance fields. Once you've done this, something almost magical becomes possible. To find the blue mug, you take the text blue mug, run it through the same foundation model to get its feature vector, and then ask the 3D field, which regions have features that point in the same direction as this text? The regions that light up, measured by cosine similarity, are literally the 3D location of the object you described, even though nobody ever trained the system on the category blue mug. You've built an open vocabulary, language-queryable 3D map. The robot can now be told about objects in plain English and locate them in space. For an embodied agent that has to bridge language instructions and physical action, this is close to the whole ballgame. The costs are real. Those feature vectors are high-dimensional and expensive to store and render, so a lot of work goes into compressing them. And the semantics are only as good as the 2D teacher model. But the direction is unmistakable. Geometry and meaning fused into one differentiable 3D representation, queryable by language. Structured representations, 3D scene graphs. Let's zoom out, because there's a whole dimension we've been ignoring. Every representation so far is essentially a big, undifferentiated field of geometry, a soup of points, voxels, or Gaussians. But that's not how you think about a room. You don't hold 3 million surface points in your head. You think, this is a kitchen. It contains a counter. The counter has a mug on it. The kitchen connects to the hallway. You think in terms of objects and relationships, a structured, hierarchical, symbolic model. That's what a 3D scene graph captures, and it's a completely different and complementary kind of representation. A 3D scene graph is exactly what it sounds like, a graph where the nodes are meaningful entities. The building, its rooms, the objects in each room, and the edges are relationships between them. Contains, is connected to, is on top of, is near. Crucially, it's hierarchical. At the top, a building. Below that, rooms and places. Below that, objects, each with a position, a category, maybe a bounding box or a mesh. It's a layered abstraction of the same physical space, from coarse to fine. Why does an embodied agent want this? 3 reasons. First, planning. Navigating "go to the kitchen" over a scene graph is trivial. You traverse a handful of room nodes, whereas planning that same route directly over a million voxel grid is enormously more expensive. The graph gives you a compact, high-level map to plan on. Second, reasoning and language. Bring me the mug that's on the kitchen counter maps directly onto graph structure. Object node, mug. Relationship, on. Object node, counter, inside room node, kitchen. Language and symbolic reasoning fit graphs like a glove, which is exactly why scene graphs pair so naturally with large language models driving robots. Third, memory and scale. A scene graph of an entire building might be a few thousand nodes, laughably small, while the dense geometry would be gigabytes. You keep the heavy geometry only where you currently need it and carry the lightweight graph everywhere. Now, a scene graph doesn't replace geometry, it organizes it. In a well-designed system, the graph is the high-level index, and each object node can point down to a detailed geometric representation, a mesh, a set of Gaussians, a feature field, when fine manipulation actually requires it. This layering is, I think, where the field is heading. Symbolic structure on top for reasoning and planning, rich differentiable geometry underneath for perception and action, semantics threaded through both. That combination is what lets an agent understand a command, plan across a whole building, walk to the right room, and then grasp the specific object, all from one coherent, multi-level model of the world. How to choose, matching representation to task. We've now toured the whole landscape, so let's make it practical. How do you actually choose a representation? The honest answer is, it depends entirely on what the agent has to do, and the best real systems mix several. But here are the decision rules I'd carry in my head. If the task is navigation, getting from A to B without collisions, you want a representation that makes free space explicit and is cheap to query. Occupancy grids, octrees, and ESDF-style distance fields are the classic, battle-tested answers. You do not need photorealism to avoid a wall. You need fast, reliable, is this cell free queries. Keep it lightweight. If the task is manipulation, grasping and moving objects, the demands flip. Now you need high geometric precision right at the surface, ideally with the ability to reason about specific object shapes. Signed distance fields, meshes, and increasingly neural or Gaussian object models shine here because grasp planning lives or dies on accurate local geometry. If the task involves language and open-ended interaction, find the thing I described, you need semantics fused into 3D, feature fields and semantic maps, very likely sitting on top of a scene graph so the agent can reason symbolically about what you asked. And if you need photorealistic reconstruction or simulation, say building a digital twin to train the agent or rendering novel views, NeRF and especially Gaussian Splatting are your tools because they're differentiable and they look real. Now overlay the practical constraints. Real-time, on-robot compute pushes you toward explicit, fast-to-query structures and away from heavy per-query neural fields, which is a big part of why Gaussian splatting caught fire. It kept the realism but recovered the speed. Dynamic, changing environments remain genuinely hard for every representation on this list. Most were designed for static scenes, and handling motion is an active research problem. And memory forces the eternal trade between detail and scale. Step back and you'll notice the field is quietly converging on a pattern rather than a single winner, a hybrid stack. A structured scene graph for high-level reasoning and planning, a differentiable geometric field, Gaussians or neural, for photoreal perception and precise action, and semantic features threaded through the whole thing so language can address any level. No single representation wins the scorecard on all 6 axes. The art is in composing them. Frontiers and outro. Before we wrap, let me point at the horizon because this field is moving fast, and the open problems are exactly where the exciting work is. The biggest one is dynamics. Almost everything we discussed assumes a frozen world, but real environments have people walking, doors opening, objects being moved by the robot itself. Representations that gracefully handle a changing 4D world in real time are still largely unsolved, and it's arguably the central challenge for deploying embodied agents in the wild. Second is uncertainty. A good agent shouldn't just hold a model of the world, it should know what it doesn't know, which regions it hasn't seen, which estimates are shaky, so it can explore intelligently and avoid confidently walking into a space it never actually observed. Baking calibrated uncertainty into these rich neural representations is very much open. Third is scale and lifelong mapping. Representing a single room is solved many times over. Representing an entire building or a city and updating it over days and weeks as things change without the memory exploding or old knowledge rotting, that's a different beast. And fourth is the deep fusion of geometry, semantics, and action into a single learned representation, one that a robot can perceive with, reason over in language, and directly plan actions in, end to end. Every piece we discuss today is a step toward that unified world model, and it's genuinely one of the most important open problems in embodied AI. So let's bring it home. We started with a robot trying to fetch a blue mug, and we saw that hiding behind that simple request is the question of how a machine represents three-dimensional space. We walked from explicit point clouds and voxels through the elegance of distance fields into the neural revolution of NeRFs and occupancy networks, over to the real-time realism of Gaussian splatting, up into semantic feature fields that fuse language with geometry, and finally to scene graphs that give the whole thing symbolic structure. And the punchline is that there's no single right answer. There's a scorecard of trade-offs, and the best embodied agents compose several representations into a layered stack. If this gave you a clear map of the territory, that's exactly what I wanted. The representation is the quiet foundation everything else stands on. Get it right, and perception, planning, and action all get easier. If you found this valuable, subscribe because we go deep on this stuff. And let me know in the comments which representation you'd want to see a full standalone deep dive on. Thanks for watching, and I'll see you in the next one.